So hey everybody, my name is Colin Dixon. I am the chair of the Technical Steering Committee for OpenDaylight. I'm also a distinguished engineer at Brocade, and for the purposes of this talk, I also have a PhD in distributed systems, which is true in general, but in this talk is actually relevant. So I think lots of people are going to be interested about clustering in OpenDaylight. The slides are a nice pathway that we can take. But I know about 17,000 times more about OpenDaylight clustering than we can get done in half an hour. So if you have questions, just go ahead and ask. And I'll control my time. I promise you that I'm louder and better at controlling time than you are. So the first thing I wanted to add is that none of this work is code that I actually wrote. That is actually true. None of this talk is about code that I actually wrote. Moyes and Tom P. wrote almost all of this code. So everything that's good about it is code that they wrote. Everything that's bad about it is probably my fault. So you can take it that way. So you've probably seen some version of this architecture for OpenDaylight. The general idea is that you have sort of, northbound applications. They talk to OpenDaylight through a variety of northbound interfaces, whether it's REST, RESTconf, netconf, or whatever. You have a variety of southbound plugins, and they speak to devices at the bottom. If you haven't seen this architecture already, go look at the OpenDaylight website. You'll find one. That's a little bit of a lie if you look at how the software architecture is, though. I mean, that's a good logical architecture. It's how I think about OpenDaylight. But the reality is that sort of everything is a service running on top of the MDSAL. And so the southbound devices and plugins are all dangling off of that. Applications are dangling off of that. And really, because that is at the bottom of everything, this tiny little arrow, you can see that I have a couple of them drawn out, that's clustering in this diagram. So you can run multiple copies of the underlying MDSAL and the applications on top of it. And you can get scale out, high availability, and all of the normal things that you would expect from clustering. And so this is sort of how it ties into the architecture. Essentially, we just stamp out lots of copies of OpenDaylight. And at least in Beryllium, we don't really make the assumption, but in practice, they're identical copies, running identical sets of code, running identical copies of the application. There's nothing fundamental about the infrastructure we've built that means that has to be true. It happens to be true because that's the first thing you build. So most of this talk, I'm going to talk about the data store. Because if you're not talking about state, clustering is really easy. It's all about shared state that makes it hard. And so the data store is where we share all of our state. The data store consists of one single tree. Everything is rooted sort of at the top of that tree in OpenDaylight. All of it's modeled in Yang. And so the first level, the first set of nodes under that root, are all of the Yang modules. If you don't know what a Yang module is, it doesn't really matter. We just have different segments of the data store, and they're broken down from one root. We break those different subtrees up into shards, and those shards are then mapped onto a subset of the nodes running OpenDaylight. And as I've said, sort of in Beryllium, for all intents and purposes, every single node is a replica for every single shard, and so they're all identical. You're just trying to get scale out and high availability in that way. There is in Beryllium, we have one level of sharding, which is to say that every child of the root is its own shard. You cannot do sharding below that. It's something which is on the roadmap. But right now, for all intents and purposes, every single child underneath the root of the data store is a shard. And if I say things that don't make any sense, please raise your hand and yell at me. Or rather, if you don't understand what I say, raise your hand and ask a question. If I say something that makes no sense, then you can yell at me. We replicate all of the shards using the Raft distributed consensus protocol. And if you spent time around SDN controllers recently, this might be familiar. Onos uses the same protocol. Essentially, Raft has become the de facto go-to distributed consensus protocol. I personally prefer Paxos, but apparently other people don't understand it. So Raft provides strong consistency. And that is to say that there is one timeline in which everybody exists, and everybody can agree where they are in that timeline. So it provides essentially the same property as if you were running on a single node from the point of view of the data store. It also provides transactional data access, so you can do snapshot reads. You can do snapshot writes, which is to say, I can write a whole bunch of data and it won't be visible until it goes there. And you can do read-write transactions. It tolerates F failures with 2F plus 1 nodes. So basically 3 gives you 1 failure, 5 gives you 2 failures. This property at the bottom is actually sort of a fundamental property of distributed consensus. You cannot have, that is the minimum number of nodes you need to be able to have strong consistency and tolerate the number of faults. If you don't want to have strong consistency, you can break that model. Right now, we have leaders handle all of the writes. This is actually a performance optimization. You can do it without that, but leaders handling all the writes. So every shard is a leader. That leader handles all the writes. That lets you have one person order everything. And it's much easier to have one person order everything than it is to have distributed agreement on sort of finding and ordering. If you're curious, you can go look at the difference between leader Paxos and Paxos. And you get about 2 or 3x performance improvement if you start doing leaders at the cost of a couple of quirks in terms of if the leader dies, you have to wait for some period of time to elect a new one. Leaders for all the shards are distributed among the nodes to try and spread load. So if you have 3 nodes and different shards have different leaders, the result is you can get 3 times the performance you would have had. If you have 5 nodes and you distribute the leaders appropriately, you can do that. Any given shard is going to be bottlenecked by the performance of a single node. And again, this is a sort of fundamental property of distributed consensus with strong consistency. If you don't want it, you can do better, and you can actually implement other things on top of OpenDaylight. But if you want strong consistency, and I'm going to make a case that you probably do, at least for some of what you do, you need to take that hit. So did that make any sense at all? Raise your hand if that made sense. OK, raise your hands if the words distributed consensus make no sense to you in general. OK, good. At least a few people are honest. OK, we've decided to use strong consistency in OpenDaylight. And not everybody has made the same decision in SDN. And I'm going to argue why I think that we're not crazy. But first, I sort of need to explain what strong consistency means. And so hopefully this will work. It's been a while since I've taught distributed systems. So serializability, which is what strong consistency is, says that there is exactly one timeline in the world, and everybody agrees at what point they are on that timeline, which can be translated to, basically, if I read a value, I will get the most recent write to that location in the data store. So not 2 writes ago, not 3 writes ago. I will get the most recent one. So that's the strongest form of consistency. It basically says that it's as though you were running on one computer, where all of the reads and writes were perfectly ordered, and so you knew what the result of every read and write would be. There's no ambiguity about, well, this could have come before that, or that could have come before this. There are 2 sort of relaxed forms of consistency that I'll talk about. There's causal consistency, which is really interesting because it still has a bunch of the nice properties that you want, but thinking about it writing code tends to be a little bit harder. So causal consistency says it is not possible that, so I see an event, any event that could have caused that event, I will have also seen. So this is, and it's sort of a theory of relativity kind of thing, where there are events which are fundamentally cannot be placed with respect to each other. So it is possible that I don't know whether that read occurred before that write, or that write occurred before that read. And as long as it's not, as long as you can't prove that one should have happened before the other, that ambiguity is OK. And this is really useful if you understand it and can exploit it. It is a much more complicated model to program in. It's basically if you enjoyed reading Einstein's theory of general and specific relativity, and you felt like you understood it before Randall Munroe wrote his piece that was recently, then this might be for you. It offers a lot of performance advantages, but it is a little bit wonkier to think about. And lastly, there's eventual consistency, which says eventually everybody will agree the same thing has happened. When they happened, we don't necessarily agree on. And when actually we all agree on the set of things that happened is also unclear. And so my joke is I usually say eventual consistency is using eventual in the same way that your kid uses it when he says he'll clean his room eventually. It's very hard to write to this. I mean, you can. There are lots of important things have been written to eventual consistency models. It involves a very deep understanding of distributed systems. So let me give you a concrete example of why you might care. Let's say that you're writing an OpenFlow controller. I know that's a really far out concept for this room. And the switch emits a whole bunch of events saying port up, port down, port up, port down, port up, port down, port up, port down. If you can't order those events correctly, and I ask you whether the port is up or down, you will not be able to tell me. And as a consequence, you might do all kinds of wonkily bad things, like not forward traffic to a host. And so this is a toy example. It is true that technically speaking, you need them to be ordered. But in this case, all of the events are happening sort of from one device, and they're coming across a TCP connection. And so unless like the switch's TCP connection fails to one instance of the controller, you fail over to the other one, and then you have to sort of, and then the events go across, background streams in OpenFlow 1.3, probably you can manage this. You keep them in the same order they came in the TCP stream. But the same idea comes up in more complex places where imagine you have 2 or 3 different switches attached to 2 or 3 different instances of the controller. They're having different port up and port down events, or the switches are going up and down. You're not going to be able to agree on the topology of the network without having some ordering to that and being able to actually, and if you can't agree on the topology of the network, you might make different decisions about reachability. So you might, for instance, accidentally violate your security policy and claim, well, I don't have to put any rules in because there is no physical path between these 2 hosts. But there is a physical path between those 2 hosts. You just don't know about it because you've been following inconsistent updates. And so these are examples why you practically, an application developer writing code for OpenDaylight, might care about strong consistency because it just makes these things go away by ordering all of the events. So if that sounds awesome, you might wonder why everybody doesn't use it. And there's a bunch of really sort of nasty drawbacks to strong consistency. Strong consistency can't work in the face of partitions, provably. If your network splits in 2, either one side has to stop, or you have to violate your strong consistency. There is no other way around it. This is the CAP theorem, for those of you who are curious. Eric Brewer first stated it, and then FLP, and now I have to remember, proved it. And it's, I could come up with their names, you gave me a second. So if you're curious, you can go there. There's also a really interesting 10-year retrospective on the CAP theorem where Eric Brewer says the CAP theorem isn't true. I think it's not that it isn't true, but it doesn't apply as broadly as people claim it does. It is true. It is mathematically provable. It will never be false. But interestingly, SDN controllers, I think, are probably one of the few places left where I think the CAP theorem applies as strongly then as it did today, or as strongly today as it did then. And I can get into that, but probably that's beyond what most of you care about. The second thing is strong consistency requires coordination. You have to order every single event that happens if you want strong consistency. And in order every single event, you need to know of every other event that's happened. And you don't have to do it by coordinating a single node. In practice, people do. And the result is that you can't go faster than a single node for things that are ordered with respect to each other. So in OpenDaylight, shards are strongly consistent within themselves. There is no strong consistency across shards. So any given shard can go as fast as a single node, but no given shard can go faster than that. And that there isn't a way around this. It's another, but it is a drawback of strong consistency. And so given these 2 drawbacks, but the pain which you get caused if you don't use strong consistency, you sort of have 2 choices when you're going about building a system like OpenDaylight. You can either make everything strong to start and relax the things that need to be fast or need to tolerate partitions, or you can make there be no consistency guarantees and try and claw your consistency back later. My personal experience is that you're better off doing the first. And so OpenDaylight started strong, which is a great phrase. I think I'm going to put it on T-shirts. But this is sort of what strong consistency is, why you might want it, and why we chose Raft. So that's the theory of distributed systems in, I don't know what that was, 12 minutes, and why it is that we made the decisions we did. The rest of this talk, I'm going to be a little bit more practical about the actual programming interfaces to use clustering. In OpenDaylight, essentially, think of service or application or whatever you want. Whatever piece of functionality you want to build in OpenDaylight, it sort of has two parts to it. There's code and there's data. This shouldn't surprise anybody. It turns out there's a third part, which is a Yang model, which is a description of what the data is going to look like. It's just a schema. We run one instance of the code on each stamped out instance of OpenDaylight. And then we try to co-locate the running code with the leader of that shard for which the data is there in order to improve performance. And we only use the data store for exchanging and synchronizing state. That's not to say that we prevent you from doing it, but if you don't use the data store as your only mechanism of exchanging state, all of the nice properties I described about clustering don't apply to you. If you go outside the bounds of what we understand and try and send messages, you can screw yourself up however you want, or you can relax the consistency guarantees. That's sort of your take. And so in this way, you just get the single common data store abstraction. You can read and write data, but not everything is data in OpenDaylight. So there are lots of things which are events. I think I've said this, and I'm going to stand by it. There's 4 kinds of events in OpenDaylight. There's notifications, there's data change notifications, there's routed RPCs, and there's global RPCs. And so we've built a whole bunch of tooling around this to help people build applications and get things to work correctly. So we have an entity ownership service. And that basically is just, there is a string, and only one OpenDaylight node can own that string at any given point in time. So you can basically say it's just a mutex across the entire controller cluster. But you can query who that's supposed to be. And the result is you can make sure events for some entity. An entity can be an OpenFlow switch, whatever you want it to be. In the OpenFlow plugin, we use it for per switch. All the events for that entity can be handled on one particular place, so you know where that place is. If that place goes away, like for instance that node crashes, you can change the place where that's supposed to go. The result is you can deliver all the appropriate messages, events, notifications there. And similarly, and sort of loosely coupled to the data store, there are data change notifications. They are delivered, and I guess I can just pull this up. Here are the 4 kinds of events. Data change notifications, you can have delivered wherever you want. So we have there's one way you can have them delivered, which is just the leader of the shard. And so you can choose that to be coupled with the entity ownership service. That way, basically, all notifications, all writes, everything goes to exactly one person. This is in practice how most people seem to use it. We have Yang model notifications, which are delivered locally. This is really, really useful for things like events coming up from protocol drivers, where you really want to have all of the logic for one particular managed device happen on one node. The notification comes up, you raise it locally, you don't have to worry about sending it across the controller. We have global RPCs, which behave in a similar way. They're just delivered locally on the same node. We assume that global RPCs are basically implemented everywhere. Everybody has them. And then we have routed RPCs, which are specifically, essentially, if you're trying to target an entity. If you're trying to target a particular OpenFlow switch, you can send a routed RPC to that OpenFlow switch. It will go to the right node in the cluster. So you can essentially send these events to the right place. So here's a quick example. Let's say service X is like an L2 switch application, and it's trying to write to the OpenFlow plugin, which we'll call service 1. So the first thing which it does is it's going to resolve basically who it's talking to. And that's just going to be by who it talks to in the data store. That's going to go to a certain shard, and that's going to tell it where to go. And that's going to take it to the leader of the shard, which is going to be co-located with the code that runs the OpenFlow plugin. And so that's 1. 2 is, if it does any reads, it's going to go to the leader. We're working on the performance enhancement of being able to do reads locally to the follower. It changes the consistency model a little bit if you do that, and so it's not done by default. Writes are sent to the leader, and they always have to be sent to the leader to be ordered, and that is not going to change. Notifications, if you do a write, are going to be delivered locally to that node by default, but there is essentially a clustered data change listener which let anybody in the cluster listen. You can use this to build sort of, applications that run across the entire cluster. And so this is a pretty common pipeline of sort of, one service calls into another service, looks up who it is, finds them in the data store, and sort of exchanges information in this way. Any one of these nodes could fail, and it would just result in the functionality being migrated to one of the other nodes. So I've talked. Talked about all of this. I talked about this a lot, talking about Beryllium. In Beryllium, we had some really huge upticks in clustering. The two biggest ones in terms of the underlying infrastructure were we implemented the entity ownership service, which was really in response to applications trying to work with clustering and finding that they needed additional support. So this is more application support to make it work. We added clustered data change listeners, which let you essentially subscribe to events in the data store everywhere as opposed to just on the leader. And this has all been to support significant sort of application adoption. So the OVSDB project, including its network virtualization, the OpenFlow plugin, the netconf plugin, the OVSDB plugin, the Neutron sort of API adapter, all of these were moved to working with clustering to be fully highly available. And we test them in our continuous integration pretty much every time. And I think Luis, if you're curious about clustered testing, Luis is somewhere in the room and he'll talk to it. There. And so this is really what changed, I think, in Beryllium was that in Lithium, we thought we had all the primitives we needed. And we weren't technically wrong. But in Beryllium, we had people actually try and write applications that were highly available. We discovered that there was some syntactic sugar that probably should have been there to begin with. And we've added a bunch of that and tried to simplify other things. And the good news about this is that there are now examples of how to essentially build clustered, highly available applications in OpenDaylight that you can go look at. So the current work that we're doing, I think really there's two areas of work that we're currently working on. One of them is dynamic multi-level sharding. And so this is the idea that right now shards are statically defined when OpenDaylight boots, and they're only sharded at one level, the Yang module level, one level below the root of the data store. We'd really like to be able to pick different sharding levels for different applications, and we'd like to make it potentially dynamic, which is to say, have it change at runtime. There are a bunch of complications in that, but some subset of that is probably going to be implemented in Boron. We're also trying to improve performance, scale, stability, et cetera, as always. There's two concrete things in that space. One of them is to allow faster, but I say stale, reads from your local replica. And so this is, if you're not on the leader, you can do a read, and it will return instantly as opposed to going to the leader. The disadvantage of that is that if you remember correctly, I said that strong consistency said there was one timeline, and everybody agreed where we were on that timeline. Stale reads say there is one timeline, and you will never go backwards on it. But you might be at a different point than everybody else. And so if you allow people to exist at different points but on the same timeline, you can get better performance. But again, it starts meandering into that area where if you like relativity, it's fun. Otherwise, it can be confusing. The second thing is to allow pipelining for higher transaction throughput. Right now, essentially, we only have one in-flight transaction at a time. And this makes the performance when clustered noticeably worse than when not clustered, which isn't fundamentally required. And lastly, whatever else you're interested in helping with, we would love to have more people come and help write this code. And the people who write it and work on it are really nice people. I like them a lot. So if you come and show up, they'll be friendly to you, I promise. And I'm just going to end with sort of longer term plans. This is not things we're actively working on now, but we've definitely discussed, which is adding helper code for building sort of common app patterns. So this is like, it'd be really nice if you could just say, I want my app to be highly available, run it one time, fail to a different place if it is there, rather than having a whole bunch of boilerplate code that goes around it. It's not that hard to get it there, but it's probably a couple hundred lines of code you have to copy from somewhere. And And there are other models you might imagine you want to run other than run once. You might want to run everywhere, but have internal failover of what you're responsible for. We'd like to allow for other consistency models, and we do allow for that now. It's just that you have to do it on your own. So you can send messages. So like on your own, there are plenty of good ways to do it. You can keep state out locally so that we can use scratch space instead of putting it in the data store. And so applications that really care about performance have basically bifurcated their state into one set of state they keep locally just in memory and scratch space, another set of state they actually care about being distributed and shared. And so in that way, and you're relaxing your consistency model by saying, this stuff I really care about the strong consistency, the other stuff I don't. But giving more hooks and more general ways to do that, so that way we could make it work in OpenDaylight, I think would be really useful. The ramifications of doing that are really complicated because if I'm a strongly consistent service that depends on you and you've decided to be an eventually consistent service, all of my ordering guarantees about events as they came up are now out the window. And getting them back is incredibly complicated, so impossible. Maintaining controller-wide or system-wide invariance about consistency is very difficult in the face of doing relaxancy models. And lastly, federated and hierarchical clustering we've talked a lot about, and it's definitely on the roadmap, but there hasn't been a ton of, there's been almost no code in this area. The SDN interface application project has sort of basically put BGP to exchange topology information back and forth between two different OpenDaylight nodes. And that's about as far as sort of federation of OpenDaylight has gotten. But I think we're just waiting for the right people with the right use cases in order to go push on that. So that's clustering sort of theory, practice, ugly details in OpenDaylight in, I think that's just under 30 minutes. So, and I'll take any questions now or later.
Hey, Colin. This is really just a minor comment, but yeah, dealing with the ramifications of that is hard in theory, but it's not likely that your system is so chaotic that you're not going to know that you're depending on, you have strong consistency and you're depending on something that has eventual consistency. You're probably going to know that. So you would architect your system to not depend on something that is less consistent than you.
And I think that's true in any given instantiation. So OpenDaylight is a platform for, it's not really an SDN controller. It's really sort of an erector set to build your own SDN controller. And so in any given instantiation of that erector set, I agree that straightforward analysis will probably let you know when you've run into that problem. Making it so that way the erector set makes you less likely to shoot yourself in the foot with that thing is, I think, what's really hard, which is, yeah, I mean, and then different applications. For example, you have to start doing things like saying Colin's service is expecting all of its inputs to be strongly consistent. And so even if you need better performance from one of my things, my code might actually behave incorrectly if you relax it. So like I might depend on OpenFlow plugin. You might say, well, I want better performance from OpenFlow plugin, so I'm going to reduce its consistency model to eventual. Now you don't know whether or not Colin's service is going to work or not, because I wrote it expecting strong consistency. And if you're a vendor trying to ship a product, or you're a customer trying to assemble pieces, that gets complicated. I mean, it's not that you won't know, it's just, you might have to go re-implement something.
Two questions, both of which are pretty specific for
Sure.
OpenDaylight. The first is, what is the purpose of the toaster shard?
Demos? No, I mean, so we have a toaster model, which is basically just sort of, and I wish it was simpler, but it's theoretically the simplest model that you can want to play with. So you can do really good demo code with it, and it doesn't need to be performant or production ready, so you can write simple demo code. That's why it's there.
Okay, thought so, but I was just confirming. Okay, and the second one is, for clustering, you are currently using ports 2550, 2551, 2552, 7200, and 12001. What are the justifications for that? And you seem to, upon further analysis, not be using 7200 or 12001 despite listing them.
So OpenDaylight is an ongoing volunteer effort to catalog ports. I think the short version is that for the ones we do use, it's Akka. We use Akka as our underlying messaging system, and it also provides persistence. And so we used to have an older version of clustering that depended on J groups, and then we had an additional piece that was using 0MQ. I believe those are both dead. So I believe we can probably remove 2 or 3 of those 4 ports, and whatever Akka requires is all that it requires.
I just wanted to reaffirm your statement you made concerning a strong consistency. So for an application, say in a VLAN configuration, strong consistency, is impractical. Is that accurate?
So the question is, if you were trying to configure VLAN, strong consistency would be impractical. Is that, and I think the answer to that is no. So strong consistency, if you wanted to update your VLAN configuration, despite the fact that your network might be split in 2, strong consistency would be impractical because essentially you wouldn't be able to confirm that the update was the same on both sides. So you want to move VLAN 12 to VLAN 15, and your network is divided in 2. There is no way I can fix that, so that way you can know that you're moving VLAN 12 to VLAN 15 on both sides, unless you can talk to each other, at which point there's not a partition. And so that's what the strong consistency requirement is about. Does that help?
Hi, what kind of features are being looked at for Boron? Because we are trying to simulate a 3-node cluster, and we have a lot of issues like read from follower failing, and shard leaders being in different nodes. So is there? So
if you have bugs to file, I would encourage you to come file them. We certainly had more than our fair share of bugs fixed in the 4 weeks running up to the release of Beryllium. And Luis can comment on this. I mean, we went from, we now, at least in our setup in our lab, consistently, despite pretty intensive ways of trying to get it to fail, get it to pass. I wouldn't say that it's perfect. I mean, my guess is there are still corner cases. Writing distributed systems stuff is notoriously difficult, and the only way you find out what's wrong is either by proving the correctness of your distributed system, which some people have started to do, and I'd be curious to see if you can do that with OpenDaylight, or by just testing the ever-living bejesus out of it and handling bug reports seriously, which we do.
Yeah, I just want to add that today in OpenDaylight we have continuous integration cluster tests for at least OpenFlow and OBSDB. And this is really a high availability test where we are breaking the leader, we are breaking really the instances. And one of the things we figured out is sometimes it takes some time for the new leader election. This is something that people ask me all the time. Today there is some timer, I don't know, I need to investigate with the developers. It's like 10-second time,
so
kind of, when you actually...
So I think there's something, there are 2 things that can go wrong. Yeah. You can have no leader for some period of time because they die and you have to wait for them to be dead. And the second thing which can happen is that you can have, if you bring up your cluster in not the same, so if you bring up 2 nodes and you bring up a 3rd node, it's possible to end up with 2 clusters. And that they shouldn't pollute each other, and you can get the Akka config in order to stop them from happening. But this is sort of a classic problem with clustering, which is you end up with more than one cluster if you don't have them all start off knowing about each other. And I think that there are, I'm 99.9% sure that if you get your akka.conf file right, that can't happen. There's a separate problem, which is, and this is a problem with a bug in Akka, we have a bug filed against it, which is if the first Akka peer listed when you boot isn't up, you will not join the cluster. Why it is that's done in Akka, I have no idea. But we've started to get Akka to take us seriously and start fixing some of these bugs.
So have you guys went through the same kind of like evolution in providing an redundancy-based HA, which is basically one of the major issues with redundancy-based HA is split brains. Mm-hmm. Do you handle split brains today?
Well, we handle split brain by being strongly consistent and basically claiming that you can't have 2 halves of you exist. So 1 half will stop. in the way we've implemented it right now.
Well, I mean, split brain, one of the major issues in split brain is that I don't know what is the status of the other side because I lost communication with it.
Yeah, no. And so okay. So in OpenDaylight, we use Raft. Raft has strong consistency. And so as a consequence, if you have 3 nodes and it's split 2 on one side and 1 on the other side, you need to get 2 votes for something for it to happen. So the side with 1 node is going to be unable to get anything to happen. And so you will know his state because his state was whatever his state was when the partition happened because he is not allowed to make progress. That's what? So yeah, we don't support a cluster of 2. Okay. We support only 3 nodes worth of clustering. And this is, and you know, you could certainly relax it. And you know, I think there are people that have done it. But we chose to try and do the thing which makes the programming model sanest.
Just a small comment to the previous question and to what you just said, Colin. The upgrade to akka 2.4.1 has been done, I think, last week for Boron. So you know, some of the issues that we've seen with akka probably will go away in Boron. The other thing that is going on in Boron is that may solve your problem is kind of a configuration file where you will be able to specify which shards do you want to have to behave like one entity, so they fail over all the time and they're always on the same leader. Another important thing that is coming in Boron is a so-called singleton application where you will be able to just bring up 1 instance of application per cluster. So these are kind of things that will help some of the issues that you have seen.
Yeah.
So what is the timeline?
Boron.
September 8th?
Yeah, whenever you come and help us build it. No, I mean, September 8th is the Boron deadline right now.
Okay, last question.
Give me a moment, I just forgot it. All right. When doing clustering, if we've seen that when nodes go down, there is a particularly high burst of traffic between the nodes when you are reestablishing their existence in the cluster. And is that due to the persistent writing and reading back from the storage and synchronization of transactions?
My guess is it's just recovering the data that happened since it was last connected. But if it's more than that, I'd have to go look at it. I don't know. But that behavior would be pretty common for we have, you know, there have been 2 megabytes worth of data written since you were last connected. You need to get it somehow. And so when you connect, we're going to slam it at you. That would be my guess. If it's more than that, then we should look at it and figure out what's going on.
Thank you very much, Colin.
Cool. Probably seen some version of this architecture for OpenDaylight. The general idea is that you have sort of, you know, northbound applications. They talk to OpenDaylight through a variety of northbound interfaces, whether it's REST, RESTconf, NetConf, or whatever. You have a variety of southbound plugins, and they speak to devices at the bottom. If you haven't seen this architecture already, I go look at the OpenDaylight website. You'll find one. That's a little bit of a lie if you look at how the software architecture is, though. I mean, that's a good logical architecture. It's how I think about OpenDaylight. But the reality is that sort of everything is a service running on top of the MDSAL. And so the southbound devices and plugins are all dangling off of that. Applications are dangling off of that. And really, because that is at the bottom of everything, this tiny little arrow, you can see that I have a couple of them drawn out, that's clustering in this diagram. So you can run multiple copies of the underlying MDSAL and the applications on top of it. And you can get scale out, high availability, and all of the normal things that you would expect from. This might be familiar. ONOS uses the same protocol. Essentially, Raft has become the de facto go-to distributed consensus protocol. I personally prefer Paxos, but apparently other people don't understand it. So Raft provides strong consistency. And that is to say that there is one timeline in which everybody exists, and everybody can agree where they are in that timeline. So it provides essentially the same property as if you were running on a single node from the point of view of the data store. We also, it also provides transactional data access, so you can do snapshot reads. You can do snapshot writes, which is to say, I can write a whole bunch of data and it won't be visible until it goes there. And you can do read-write transactions. It tolerates F failures with 2F plus 1 nodes. So basically 3 gives you 1 failure, 5 gives you 2 failures. This property at the bottom is actually sort of a fundamental clustering. And so this is sort of how it ties into the architecture. Essentially, we just stamp out lots of copies of OpenDaylight. And at least in Beryllium, we don't really make the assumption, but in practice, they're identical copies, running identical sets of code, running identical copies of the application. There's nothing fundamental about the infrastructure we've built that means that has to be true. It happens to be true because that's the first thing you build. So most of this talk, I'm going to talk about the data store. Because if you're not talking about state, clustering is really easy. It's all about shared state that makes it hard. And so the data store is where we share all of our state. The data store consists of one single tree. Everything is rooted sort of at the top of that tree in OpenDaylight. All of it's modeled in Yang. And so the first level, the first set of nodes under that root, are all of the Yang modules. If you don't know what a Yang module is, it doesn't really matter. We just have different segments of the data store, and they're broken down from one root. We break those different subtrees up into shards, and those shards are then mapped onto a subset of the nodes running OpenDaylight. And as I've said, sort of in Beryllium, for all intents and purposes, every single node is a replica for every single shard, and so they're all identical. You're just trying to get scale out and high availability in that way. There is, in Beryllium, we have one level of sharding, which is to say that every child of the root is its own shard. You cannot do sharding below that. It's something which is on the roadmap. But right now, for all intents and purposes, every single child underneath the root of the data store is a shard. And if I say things that don't make any sense, please raise your hand and yell at me. Or rather, if you don't understand what I say, raise your hand and ask a question. If I say something that makes no sense, then you can yell at me. We replicate all of the shards using the Raft distributed consensus protocol. And if you spent time around SDN controllers recently, so hey everybody, my name is Colin Dixon. I am the chair of the technical steering committee for OpenDaylight. I'm also a distinguished engineer at Brocade. And for the purposes of this talk, I also have a PhD in distributed systems, which is true in general, but in this talk is actually relevant. So I think lots of people are going to be interested about clustering in OpenDaylight. The slides are a nice pathway that we can take, but I know about 17,000 times more about OpenDaylight clustering than we can get done in half an hour. So if you have questions, just go ahead and ask. And I'll control my time. I promise you that I'm louder and better at controlling time than you are. So the first thing I wanted to add is that none of this work is code that I actually wrote. That is actually true. None of this talk is about code that I actually wrote. Moyes and Tom P. wrote almost all of this code. So everything that's good about it is code that they wrote. Everything that's bad about it is probably my fault. So you can take it that way. So you've